Okay, so look, I feel a little bit of a fraud giving you a lecture on Landau-Ginzburg-Devonshire theory because, number one, I'm not a theorist, and number two, I'm certainly not a world expert on Landau theory. What worries me slightly is that Jirka is, and he's sitting in the front row ready to pounce. Okay, so but I am motivated to give you this lecture. If you've done Landau theory before, then you'll see nothing new here. But if you haven't, or if it hasn't been sort of broken down into its very nuts and bolts, then I think this is a good opportunity to get a very complete basic understanding of what's going on. Okay, so why I'm motivated to talk about this is I mean, I'm going to say it's primarily because of Eckhart. It's not primarily, but it's because 40 years ago Eckhart gave me a series of lectures, and I say me. That sounds like, oh, it was all addressed to me, but the truth was that in my final year mineral sciences class, there were 4 people, and quite often the other 3 didn't turn up, especially on a Saturday morning. So quite often it really was Eckhart teaching me stuff. He taught me Landau theory. I didn't follow a theoretical route, but it has nevertheless been a lifelong framework which has been extremely useful for thinking about ferroelectrics and thinking about phase transitions. And so that's the kind of thing I'm trying to achieve today, is to give you that framework for thinking. Okay, so we've got a few things going on. The first thing is ferroelectricity. The second thing is phase transitions. And then the third thing is LGD theory. So just so we know where we are, let's first of all address what a ferroelectric is. And I'm not trying to patronize you, I'm just starting at the very start. Okay, so ferroelectricity, about 100 years old, discovered by this man Velicek, whilst working, I think, in Penn State. A thesis was published in 1922, but I think there was a paper that I haven't had access to in 1921 where this discovery was initially reported. And the discovery was as follows. So he was mapping piezoelectric properties of materials, but found in Rochelle salt that the polarization as a function of electric field had this hysteresis which had never been seen before. And the product of the hysteresis really was that if you go to very large negative fields and then reduce the magnitude of the field towards 0, you end up with one particular value of polarization at the 0 field. But if you do the opposite and go to very high positive fields and then reduce the magnitude of the field down to 0 again from the other side, if you like, one ends up with a different value of the remnant polarization at 0 applied field. So there's something going on here that is not normal in a piezoelectric, and because this hysteresis looked very much like what was seen in ferromagnetism, Velicek and others decided that they would call this ferroelectric, and it stuck. Despite the fact that there's no iron anywhere near this, but still, you know, we've got a good name, so we're going to stick to it. And really based primarily upon this observation of hysteresis. Okay, so that's ferroelectricity. We'll come back to that in a second. But now let's talk about the aspect of ferroelectrics undergoing phase transitions. And I want to show you this rather beautiful video, not mine. This is a video from Mike Glaser from his time in Oxford. And he's looking at barium titanate under cross polars. People don't really do transmission optical microscopy anymore, but if you do, it's a beautiful art. If you don't, what's happening here is there's transmitted light coming from the bottom to the top. There is a polarizer on the bottom, so it's polarized light, linearly polarized light coming in through the crystal. And then there's a cross polar above, meaning that if the light is unaffected, then there's going to be no propagation of light. However, when it goes through the crystal, and if the crystal has an anisotropic optical indicatrix, then there are magical things that go on. So in order to obey Maxwell's equations, the light must split into 2 different parts generally. And in these crystals, there is a speed difference between the 2 parts. So when they recombine, there's an effective polar rotation. And that gives you these beautiful colors. So what we're going to do, but crucially, what it indicates is that we do not have an isotropic optical indicatrix that one would normally associate with a cubic material. Okay, so this is non-cubic. And now we are going to heat it up from room temperature all the way to its Curie temperature of about 120, 130 degrees. And I should really have saved this one for the next lecture on domains, because the most dramatic thing that's going to happen here is below TC. So we'll see that first. So we're now, the temperature is 80, 90, 90 coming up 100. Bang. Okay, I want you to ignore the really cool thing. So the really cool thing there, obviously, is that you've got some optical effect, which has resulted in this beautiful Forsbra pattern. We can talk more about that on Friday. But what I want you to instead focus on, suspend that beautiful thing, and focus on the fact that now, at 180 degrees centigrade, bar a little bit of strain contrast that's kind of warping the optical indicatrix a little bit, you can see that there is no birefringence. Okay, so we have gone through a phase transition on heating where it was anisotropic, the indicatrix of the material was anisotropic, and now it's become isotropic. And that is coincident with the phase transition between it being ferroelectric and being non-ferroelectric or paraelectric. Okay, so in all of this discussion, it's really the paraelectric to ferroelectric transition that we're going to focus on. Okay, so what's happening in the barium titanate? It's definitely not what I'm about to show you. Okay, this is one of the crimes of ferroelectricity. I'm going to show you a cartoon of what's happening. Barium titanate is definitely not the right system to compare this cartoon with. It's much more complex than it seems. And instead, let's think something like lead titanate. Nevertheless, barium titanate has a perovskite structure a little bit like this. So in the high temperature phase, in the paraelectric phase, which is represented here, we have a series of cations. These would be, they would be barium, but let's pretend they're lead instead. The still cation in here would be titanium. Whoa, I knew I was going to do that. And then oxygen's red, because oxygen's always red. And what's happening here, it's like electrons are green. So what's happening here is that we have a center of positive and a center of negative charge that are coincident. So if we plotted the center of positive and negative for this unit cell, they would both be in the same place. That's the paraelectric state. Something happens on cooling, and there's a relative shift in the cations and ions in this lattice. And that relative shift in lead titanate, for example, would create then a separation between the geometric center of negative and the geometric center of positive charge that would induce this, the formation of this dipole. Okay, fine. That's not quite some minor details. So the dipole moment is going to be the charge times the separation. The polarization is the dipole moment per unit volume. And so this is the dipole in one unit cell if you want to have the dipole moment per unit volume divided by the volume of the unit cell. Rather neatly, the dipole charge here is in coulombs. This is in meters. Obviously, this is in meters cubed. When you dimensionally analyze this value of polarization, you find that it's coulombs per square meter, which is rather, I think, counterintuitive. So it's a charge per unit area, despite the fact that you're calculating a polarization per unit volume. And that gives away a little bit about how you would go about determining what the polarization value is. And typically what you do is you have a ferroelectric that looks like this with its polarization perpendicular to a surface, and you measure then the bound charge that is accumulated on these two surfaces if it's a perfect insulating system. Okay, so polarization, charge per unit area, is manifest in the way in which one would measure the polarization, but you have to choose the right surface. Okay. There's one last thing, and that is that once you've developed this dipole moment in the unit cell, that's not enough for ferroelectricity. You must be able to reverse the sense of that polarization when you apply an electric field. So when you apply an electric field, that relative shift in the sublattices has to be reversible. Okay, but once you do those things, you have genuinely created a ferroelectric system. Okay, so that's what a ferroelectric is. That's what a phase transition in a ferroelectric is, and we're particularly focusing on the phase transition from an isotropic cubic into a non-isotropic tetragonal system in that example. Okay, so now let's start to develop ideas that are related to Landau theory. There are two key things that you need to be in charge of here, and I'm sure you've all come across this before. So the two key things are, number one, the free energy. So the free energy is a construct that is a measure of a system's capacity to do work. If a system has a high free energy, it has a high capacity to do work, and therefore a high propensity to change its state of being by doing work. So high free energy, high propensity to do work, high capability to do work, high propensity to change. Low free energy, a very low capacity to do any work, therefore a very low capacity to make any change spontaneously, and therefore stable. So we equate high free energy with instability and low free energy with stability. The upshot is that systems will always tend to spontaneously change in a manner that reduces their free energy. Okay. Now, how you construct the components that go into an expression of the free energy is kind of up to you. You can go on forever. So I have this, there's a thing where you say, okay, I'm going to put a pen over here on this platform. Tell me what the energy of the pen is, right? And you're going to go, oh, well, maybe it's mg delta H, so maybe the potential energy from there to the ground, right? But then maybe there's chemical energy in the pen. Maybe we drill a hole in the floor so it can go right to the center of the Earth. Maybe we've forgotten the kinetic energy of the rotation of the Earth and the orbit of the Earth around the sun and so forth, and so on and so forth. That is all irrelevant if the problem is what happens when I kick the pen off the desk. Okay, so there are a lot of things that would go into a free energy expression, but we're only really interested in constructing the free energy so that it has the terms that are relevant to the problem that we're dealing with. And the beauty of energy is that it's a scalar, and so we can just freely add things, take things away, not bother with certain things, like the velocity of the Earth through the solar system. Okay, so here we are. Here's our ball sitting on a ledge. If that ball is going to do something spontaneously, the only thing it's going to do is fall off the ledge onto a lower platform. And thereby, it'll do work, whether it's useful work or whether it's just losses in terms of giving out heat or something when it hits the bottom. But that spontaneous process is always going to be such that the free energy is reduced. Okay. So here's a nice diagram. I mean, you could actually do this. This is one that I show students in Belfast. We actually compute this from knowledge of the heat capacity of water, ice, and steam, and knowledge of the entropy and enthalpy at 0 Kelvin. You can do it. So you can construct a free energy that's based just on entropy and enthalpy on the basis of heat capacity measurements, and you'll get something that looks a little bit like this. So the free energies will start relatively high at low temperatures, and then curve off typically in that sort of function. And the only reason I want to show you this is, look, we know that H2O has various phases that are possible: ice, water, steam. We can construct the free energy for ice separately from water, separately from steam. And without ever having seen the phase transitions that are involved in H2O, we can predict exactly when they're going to happen by following the rule of lowest free energy. So over here, this is the lowest free energy. It's associated with ice for low temperatures. Then all of a sudden you reach a critical point where the lowest free energy is now taken over by water. Okay, so it's water between 0 and 100. And then at 100 degrees centigrade, the gas phase takes over as the lowest available free energy state, and so it will spontaneously change into a gas. And that is our sort of basic framework for understanding the motivation of a system, if you like, to undergo phase transitions. It's always going to change if it changes spontaneously, such that the free energy is reduced. And the only reason that you don't stick with one particular phase and have no phase transitions is that the thermodynamic environment in which the system finds itself changes. Okay. All right, and that's pretty useful. And you can see, obviously, when you look up phase diagrams, these phase diagrams represent the lowest free energy configuration for the system as various thermodynamic properties change. So as temperature changes, as composition changes, sometimes, of course, you'll see pressure and all the rest of it. But this map is the map of the lowest free energy for that particular system under those thermodynamic conditions. Okay, so what? So we're doing well. So we know what a ferroelectric is. We know that a ferroelectric undergoes a phase transition. We know what that is. We know about the free energy as a driving principle that you can calculate or construct some energy expression, which will always tend to find its minimum position under equilibrium. Okay, so the next thing then that we need to get on top of is this concept of the order parameter. So the order parameter is a parameter. And originally, I suspect, although I don't know this, but originally I suspect it was used to tell you the extent to which an order-disorder phase transition had occurred. So if you were disordered in the high temperature state and you became ordered in the low temperature state, you could express the degree to which order had developed as a fraction of its possible full development. That parameter would then be called the order parameter. But now, the order parameter is really nothing to do with order. Okay, it's called an order parameter, presumably historically, but what it does do is just gives you a normalized number between 0 and 1, where 0 is the high symmetry, usually high temperature state, and 1 is the fully transformed low temperature state. Okay, and the order parameter, for our purposes for the moment, is anything you want it to be, provided you can construct it so that it's 0 in the high high temperature state, the high symmetry state, and can be fully developed to 1 in the fully transformed low temperature state. So I'm going to show you an example here, ironically, which is order disorder, but I don't want you to get stuck in the notion that it has to be order disorder. We'll talk about other versions, cartoon versions of phase transitions in a minute that are not order disorder. So here we have a high temperature state. There are equal numbers of A and B atoms in here. And if I put my finger on any atomic site in this high temperature state, there is an equal probability that it'll be A or B. So the system is completely randomized. However, on cooling, the A's and the B's will adopt very distinct configurations such that the shortest bonds are always between A and B atoms in this particular example. So you'll have A here, A here, A here, B here, and then beside the nearest neighbors for the A will always be 4 B's. The nearest neighbor for the B will always be 4 A's. Okay, fine. How do we construct an order parameter for this order-disorder phase transition? Well, we imagine that there are very distinct sites, atomic sites, where A atoms belong, and there are very distinct atomic sites where B atoms belong. And what we're going to do is we're going to say, if an A atom is on an A site, then it's right. If a B atom is on a B site, then it's right. But if an A is on a B or a B is on an A, then they are wrong. Okay, so if I could go to the fully disordered state, then there would be an equal probability of this being a right atom or being a wrong atom sitting on a B site. If I go to the fully ordered state, then 100% of the time on a B site, you're going to get a B atom. On an A site, you're going to get an A atom if it is fully ordered. Okay, so how do you then develop an order parameter for this? This is the very simple notion of how an order parameter might work. So here we have the order parameter Q is equal to the number of right atoms minus the number of wrong atoms divided by the total number of atoms. Okay, so if I've got all of my atoms correctly located, all the A's on A sites, all the B's on B sites, then all of the atoms are R, none of the atoms are W, and so R is all of them, divided by all of them is going to give you a 1. If, on the other hand, it's fully disordered, you have the same number of right atoms and wrong atoms because it's a random chance that it's going to be an A on an A site or a B on an A site. So R minus W is going to be 0. And so if this is the fully disordered state, then the order parameter is going to be 0. Okay, so it works. Now, my point is this. This is not the order parameter. Okay, this is an order parameter that one could use to reflect the extent to which ordering has developed from the completely fully disordered state to the fully ordered state. And it works because it's 0 in the high temperature, high symmetry phase, it's 1 in the low temperature, low symmetry phase, and it'll be somewhere in between for a partially ordered version. And I want to show you this just while we're on it. So here I have a chessboard, and I've designated A sites by the blue and B sites by the white. I'm going to give this a smattering of atoms. So here are a bunch of atoms that have been put onto this chessboard. And we're going to go through, in order to determine the order parameter associated with this state, we're going to go through whether or not you've got an A on an A site, or right, a B on a B site, or right, an A on a B site, wrong, or a B on an A site, also wrong. So we just go through it and we tick them either right or wrong. There's a B on an A site, oops, B on a B site, yes. A on an A site, yes. And we go through here and mark them all as either right or wrong. And I think what's quite cool about this exercise is that if we calculate this, how many we've got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 are right. The rest are wrong. And we've got 6 by 3, 18. So 10 out of 18 are right. And that gives us right minus wrong, which will be 10 minus 8, 2, divided by the total number 18. So we get an order parameter of 0.1. Okay, I would challenge you to look at the original and tell me that that is not the fully disordered state. I mean, obviously now you know. But the point is that the order parameter gives you access to describing the state of being of a system that has partially undergone a phase transition, where just by visual, casual inspection, you wouldn't necessarily have said that this had broken the fully disordered state at all. Sure. No, we're going to come to that. We're going to come to that. So when it's 0, you've got the same number of right and the same number of wrong, okay? So if you go to an A site, you're expecting 50-50 chance of getting an A and a B, right? I think what you're getting at is, what if all of the B atoms were on the A sites? Yeah, exactly. Right, we're going to talk about that in a second, and that's that's a really profound statement. Okay, but trust me, suspend yourself. We'll come to it for a second. Okay, so I want to get over this notion that order parameter is always to do with order disorder. Here we have an example, and believe me. So this is a cartoon version of what happens when you go from high quartz to low quartz. It is hexagonal in the high quartz phase. It goes to a trigonal state in the low quartz phase. It's a displacive phase transition, so there's no quenching this really, as far as I'm aware. What changes here? So you might say, well, the area of that ridiculous shape that you've drawn has changed. Yeah, that's good. So maybe a volume might be changing in this high to low quartz transition. We could use the volume change normalized to be the order parameter. You might say that some of these internal angles have changed. Yes, we could use some change in the internal angles of the quartz structure and normalize that, and that might give us a feel for the order parameter. Or we could use something like the distances between whatever these vertices are, and that changes as you go from the high to low state. And that might be used normalized as an order parameter. And you can kind of track all of these things. So here is the quartz phase diagram. And the high to low transition here at atmospheric pressure is down here. And yeah, things change. So if we look at the volume, you have linearly decreasing volume, linear expansion, until you hit TC. And then at TC, something crazy happens. And you can extrapolate the linear thermal expansion downwards and then look at the difference between it and what has formed, normalize that, and then you can use that as an order parameter. Equally, you could do a similar trick with your silicon oxygen interbond distances. But the one that I think people have gone for here, this is from Martin Dove in Cambridge, or he used to be. The one that he's gone for here is a tilt angle. And you can see that he's multiplied, or he's taken this tilt angle normalized to the power 4, and he's claiming that that is very fundamental to the phase transition that exists within this quartz system. Don't worry about that for the minute. My point is, you can take atoms on sites for an order disorder phase transition and normalize that and use it as an order parameter, but you can use anything else you want as long as it is indicative of the phase transition that's going on. Now, it may not be...
Sorry, quick question.
Shoot.
Is it supposed to be linear? Because,
Yeah.
fits in there, and what I know of phase transitions is this diagram of, I don't know, this curved
Yeah.
transition. And I do see this curve in, for example, C.
Yeah, so normally I think, and I'm going to draw these in a minute, so normally you would expect to see the order parameter here, and you'd have like TC here, and it would come down 0, 0, 0, 0, 0, and then something would happen at this point and it'd be a curve, right? So it would curve up like this. Okay, and quite often that curve, you can get like Q squared is proportional to TC minus T, or you can get Q to the fourth is proportional to TC minus T. And those would be two very classical results. So what they've done here is instead of plotting it against Q, they plotted it against Q to the fourth. So they're automatically linearizing what they believe to be this behavior. But you're absolutely right. So this is often what you see when you develop a phase transition. It's just that they've tried to convince us that this is a Q to the fourth kind of behavior. And as you say, it curves off a little bit, so they didn't convince you very well. Okay. Oh, here it is. Okay. So in general, when you map the order parameter as a function of temperature, if you've identified what's called the primary order parameter, so if you've got lucky, then there are only really three behaviors that can happen. Either you get a sudden jump at TC from a 0 to a non-zero order parameter. That's first order behavior. Second order behavior is classically this quadratic form. And then tricritical behavior, we'll see in a minute, is exactly in between. It's the point of transition from first order to second order, and it's characterized by this Q to the fourth kind of behavior, which you would think would be extremely rare, but is actually much less rare than one might imagine. Okay, how are we doing? Good. I think we're okay. So we now have our key concepts. Shoot.
Are there any systems where instead of it kind of curving that way, it curves the other way?
Not that I've come across, but you know, there be dragons. So I think the point is that this would be the sort of classically accepted version of events, provided you have identified what they call the primary order parameter. And if you haven't identified the primary order parameter and you map something else, then that's where there be dragons. Okay, so we'll talk about that a little bit towards the end of the lecture. All right, but so far this is pretty much true. So we know what a ferroelectric is. We know what a ferroelectric phase transition is. We know about free energy, and now we know about the order parameter. Shoot.
So if I was to have infinite resolution in temperatures, all these transitions, so the order parameter is always continuous with temperature?
Yes. No. Well, the order parameter is always continuous with temperature, except for first order.
First order, it really jumps.
It really jumps, and we'll show how it works in a second. But I'm not allowed any further than that line. But at TC, there are two values of the order parameter under equilibrium for a first order. I'm looking at Jirka, but that's right. I know that's right. Okay, all right, and we'll derive it. Okay, so let's then move into the Landau-Ginzburg thing. So I think, I'm going to just call it Landau theory. That's really offensive, I'm sure. But you know, it's shorthand. So I think one of the really cool aspects of what Landau contributed here is that he realized the importance of both the free energy for mapping the equilibrium state of a system, and also the fact that the order parameter could allow you to really interrogate the extent to which a phase transition had occurred. Wouldn't it be cool, I imagine he said, if you could construct the free energy as a function of the order parameter? Because then you could find the minimum in that function, and that minimum would be the state to which the system would evolve under equilibrium. Problem is, you've no idea what this free energy as a function of the order parameter actually is. So let's imagine that it's this. If you had that, that would be great, because you could find out where the minimum value is, and you could then work out what the equilibrium value of the order parameter would be for this particular system. One thing that I want to make absolutely clear, because I fell into this trap when I was studying this stuff. This is genuinely equilibrium. So, you know, the fact that you move from a high symmetry state to a low symmetry state, and that there is some process by which the phase transition occurs. When you say process, you tend to think things developing over time. This is not anything to do with kinetics. This genuinely reflects the equilibrium value at each one of these temperatures as the thermodynamic environment is changing. There is a distinct equilibrium value for the order parameter. Okay, so it's not anything to do with kinetics, and I think that's important to feel comfortable with. Okay, so I think part of the initial genius of Landau is just asking the question, wouldn't it be great if we had the free energy as a function of order parameter, because then we could track the equilibrium value of the order parameter and maybe access some of the physics associated with phase transitions. Problem is we don't know what this is. Okay, and there I think come in two very important aspects of genius. I mean, it's not hard to say Landau was a genius. Okay, the first aspect relates to you were saying about all the B's on the A sites versus all the A's on the B sites. A's on the A sites. So here we have an example of that order-disorder phase transition where we have the fully transformed low temperature state. So all of the A's are correctly on the A sites, all of the B's are correctly on the B sites, and if we worked out our sort of dodgy order parameter version of events for this, the order parameter would be 100% right, no wrong, divided by all of the atoms gives you an order parameter value of 1. However, as you rightly pointed out, you could develop the same ordered state by putting all of the B atoms on the A sites and all of the A atoms on the B sites. And the state would be, in principle, at least in a simple case, it would be indistinguishable from all of the A's being on the A sites, now having all the B's on the B sites. The degree of order and the distribution of the atoms is absolutely identical. It's just that we misidentified the A site at the start of the experiment. Okay. But the object is the same. Yet, if we did the calculation here, we'd find that the number of right was 0, the number of wrong is all of them, and so the value of the order parameter will come out at -1 instead of +1. But they are the same state. Okay, I'm going to show you something which I think is even more convincing, and this is a non-order disorder. This is a structural collapse. So here we have a square mesh of atoms. It's going to distort a little bit, collapse a little bit as temperature is reduced. This would represent the fully transformed low temperature version of the collapsed structure. And we could track the order parameter by looking at this value delta, this angle off the vertical that this bond angle has adopted as a function of temperature or whatever the thermodynamic variable that's changing is. And the order parameter then would be normalized, so it would be delta divided by phi, happy days. In the fully high temperature, high symmetry state, delta is 0, so the order parameter is 0. In the fully low temperature state, transformed, delta is equal to phi, and therefore phi over phi is +1. Okay, but I want to make this point. Here we define phi as being a clockwise rotation of this structure. Okay, so this is positive, if you like, clockwise. Over here, we have a delta that is also positive. However, I've already defined my fully transformed state. Let's ignore that. If I look at this from the other side of the board, then delta will be anti-clockwise instead of being clockwise. Okay, so if I were sticking to my original definitions of what angles and stuff are, then what is the clockwise rotation of this new delta viewed from the other side of the board? It's minus delta. So I would calculate an order parameter of minus delta over phi instead of delta over phi, but it would represent the same state. And in a much more transparent way, I think, because here the state hasn't changed because of some conceptual jiggery-pokery to do with how you labeled A and B sites. Here, the state apparently is changing because you're viewing it from a different angle. I mean, that's not possible. Okay. So, under most circumstances, the first aspect of genius, I think, associated with development of Landau theory is that unless something else occurs, plus Q and minus Q are indistinguishable and identical, and therefore their free energies must be the same. Okay. All right. So, here's our guess at what a Landau potential might look like, and it's already wrong. Because if I go to plus Q here, I'm going to have this value of the free energy. I probably won't be able to reach to minus Q before things go wrong. But over here, minus Q clearly has a very different free energy, and so they cannot represent the same state. All right. So the other bit of Landau that I forgot to mention was that whatever the function is, doesn't matter what the function is, you can construct the value of the function at every point by doing some kind of series expansion. So you might choose a Fourier series, but in this case we're going to choose a polynomial expansion. So this is going to be equal to some parameter times the linear in Q plus Q squared plus C times Q to the cube plus D times Q to the fourth plus and so on and so on and so forth. Okay, there are some beautiful things about this. The first thing is we've defined the order parameter so that it varies from 0 to 1. And so in general, it's less than 1, in general. So this is a convergent series, okay, in the sense that Q squared is always less than Q to the cube is always less than Q squared. It's the magic of, and I still find it magical, that when you're a number bigger than 1, you square it, you get a bigger number. If you're a number less than 1, you square it, you get a smaller number. Still something magical. Okay, so this expansion, if we knew all of the prefactors A, B, C, D, E, and so on and so forth, could be used to map to any function perfectly accurately. And so, despite the fact that we don't know what the Landau expansion, what the Landau function is, we can pretend that it's this because it can be, provided you know what all these prefactors are. Okay, I should have said that earlier. Now what we know is that symmetry is demanded such that plus Q and minus Q are equivalent and therefore have the same free energy. Well, that means that you cannot have a linear term to your free energy statement because a linear term would have the free energy component as a function of Q looking like this, and clearly then the free energy of plus Q and of minus Q are not going to be the same. Okay, so any of those non-even, any of those odd exponents have to go straight in the bin, in general. Okay, that's the first, I don't know how many steps of genius there are. The next rather cool thing is to do with the mathematics of what happens through the phase transition. So let's pretend that we've got GQ is BQ squared plus DQ to the fourth as a truncated version of the simplest possible Landau expansion. We still don't know very much about it, but let's pretend we do. So under equilibrium, the derivative of the free energy with respect to Q is going to be 0. The gradient of this is going to be 0. You're at a minimum. And therefore, the derivative of our simplified Landau expansion is going to be plus 4Q cubed. And I could then factorize that a little bit and put 2Q times, where are we? And this is where I expose the soft underbelly of my mathematics live. So we got 2Q squared with, and I got that wrong already, didn't I? D. Okay. So, even already, and this is the most ridiculous simple version of how you might describe free energy as a function of order parameter. Nevertheless, already, we have solutions for when this is equal to 0. So one solution, of course, is that this prefactor could be 0, so Q could be 0. The other solution is that if this entire thing in brackets is 0, so we're going to end up with Q squared equaling minus B over 2D. So that's also a solution. So we already have two solutions, one of which we know by definition is the high symmetry, high temperature phase. That's quite a victory. And the other then must be the low temperature, low symmetry phase. Okay. All right, something else that's very cool. This is necessary but not sufficient for the minimum free energy state. This could also represent a maximum, it could represent some kind of saddle point or something like that. So, to find the full information associated with the minimum, we need to make sure that the curvature is positive through the minimum or maximum point. So we're going to look for the second derivative of the free energy with respect to polarization. That's going to be equal to 2b plus 12 dq squared. And we know that that needs to be greater than 0. Okay. And I'm going to factorize this out because I'm just a bit lazy. So this could be b plus 6d q squared. All right. we know there are two possible solutions for Q. We've got that already. Q is either equal to 0 for the high temperature, high symmetry phase, or Q is non-zero. It's this minus B over 2D for the low temperature, low symmetry phase. So let's talk about high temperature. Q equals 0. Therefore, B plus 0 must be greater than 0. And so B must be greater than 0. Okay, so B is the prefactor in front of Q squared. Now let's look at the other version of events, which is the low temperature phase, where Q squared is minus B over 2D. So now we have low temperature. Q squared is equal to minus B over 2D. Substitute that in, we get B plus 6D. So this is minus, I'm putting the minus in already. 6D times Q squared, which is B over 2D. D's cancel, that's the magic. That goes to 3, and we're left with B minus 3B must be greater than 0. Minus 2B must be greater than 0. B must be less than 0. Okay. So for the high temperature phase, we've mathematically, trivially, from this pretty blunt version of what the order parameter, what the free energy as a function of order parameter might look like, we have already come up with, number one, a prediction of the high and low temperature state, a prediction of the phase transition. Number two, we've come up with some interesting conditions for the behavior of the prefactor B in front of Q squared. And in particular, that it has to change sign as you go through the phase transition itself. Okay, and those two pieces of information lead to, I think, what is the most basic statement of Landau theory, and I'm gonna juice it up a little bit just to make life easy later on. So we have a prefactor in front of Q squared, which changes sign through the phase transition. How are we going to do that? Let's not just hold it in our heads, right? Instead, let's get it on paper. So now we're going to put a prefactor in front of Q squared, which has a constant positive factor we're going to call A. We're going to divide that by 2, and you'll see why later on. And then we're going to multiply by a toggle, which allows this prefactor to change sign. So if you're above Tc, T is greater than Tc, T minus Tc is a positive number. That allows this prefactor to be positive. If you're below Tc, T minus Tc is a negative number. That allows this prefactor to change from positive to negative, exactly the behavior that we need. It might not be linear in temperature, but for the moment, we don't care. Okay, we're throwing it together. So that's the form of our Q squared. We don't know anything about the other Q to the 4th. We don't know anything about our Q to the 6th, except that there's no Q cubed and there's no Q to the 5th. And this, if you can see that okay, because I've wrecked this whole thing, that would be, I think, the starting point for a simple Landau expression. Okay. So for the rest of the lecture, it's only 15 minutes, I'm going to show you some really cool things that pop out from this Landau expression automatically, okay? All right. The first is this. So let's consider equilibrium behavior, and then you'll see why I put on these halves, a quarters, and a sixth, and so on. So we'll go G by dq is equal to 0. So let's take the derivative. Oh, that's handy. So we end up with A t minus tc, because the 2 and the half kind of cancel each other out. And then we've got B q cubed, and then we've got C q to the 5th. And we can normalize or factorize that by taking out the q. And I'm going to rearrange it as C q to the 4th plus B q squared plus A t minus tc. And we know for equilibrium that has to be equal to 0. Oh, got to close my brackets. Okay, so either q is equal to 0, the high temperature state, again predicted, it shouldn't be a surprise. It's the same Landau expansion. We've souped it up a little bit by putting this toggle in to represent the change of sign in front of the q squared prefactor. And we've put in these halves, a quarters, a sixth to make the derivative simple. Okay, the other possibility is that this has to be equal to 0. All right, and here's a little bit of jiggery-pokery. If the A parameter is always positive, we've defined it as being positive, we use the T minus TC to make it negative. So A itself is always positive. B, we don't know whether it's positive or negative. C, we don't really know whether it's positive or negative. We don't know anything about it. Let's concentrate on the B for a moment. Okay. If B is negative, then we have a problem, and we'll see the nature of that problem later on, but we have a problem developing a physically meaningful energy function. So if B is negative, we have to incorporate a CQ to the fourth term, assuming that C is positive. And that will allow us to develop a double well potential and so on and so forth. Okay, so let's assume B is negative. So B is negative. We're going to have to deal with this quartic function, but luckily it's just a quadratic in Q squared. So we can give this, by inspection, a solution. Q squared is equal to minus B, which luckily is B, plus or minus the square root of B squared minus 4AC. So that's going to be 4 times AC times T minus TC. And we're going to divide the whole thing by, now I'm going to say 2A. But remember, A is the prefactor in front of the highest term in the quadratic, so actually A is C. Okay. All right. Okay, so some cool things here. This, if we plotted this out, this would look very like a first-order phase transition. Okay. But I want to convince you, who was it asked about the continuity of the, continuity of the order parameter? So let's consider what happens here to Q at T equals TC. So T equals TC, T minus TC, oh dear, that's TC minus TC, that's 0. So now you've got B or minus B plus or minus square root of B squared. Take the square root of B squared, you get B divided by C. So now you have two solutions, minus B plus B or minus B minus B, because there's two roots to the square root of B squared. Okay, so Q can either be, what was it? Minus B plus B. That'll be 0. Or Q squared can equal minus B minus B, so minus 2B over C. Okay, but this is at the same temperature. This is a TC. So it's not like it can be one or the other. It's both. So when you plot this out then as a function of temperature, you hit TC. You've got your Q plotted here. This is the kind of thing you were talking about. But here you've got Q equals 0 as a solution of TC, but also Q is equal to minus 2B over C is a solution. And so bearing in mind that B is negative, that means that minus 2B over C is positive. Happy days. And that then is this vertical wall of the first order phase change. Okay, this is the point that if I were Landau, and I know he has higher standards than I do, but if I were him at this point, I'd be like, wow, that is cool. I've just predicted the existence of first order phase transitions. In fact, I'm not even sure he did. You can correct me, Jirka, but I think this was Ginzburg probably did this, right?
I think he was proud of proving the second order phase.
Landau was part of the second order, yeah. So right, okay, so let's, without further ado, let's go to the second order phase transition. So in the second order phase transition, we've looked at what happens when B is negative. Now let's consider when B is positive. And when B is positive, you're onto a winner, because you've got a prefactor here which is initially positive but then goes negative below TC because of the toggle here. You've got something here which is always positive, and so even when this is negative, it can kind of counteract this positive term and give you a double well potential which is physically meaningful. So there are conditions when B is positive, you don't have to worry about that horrible quadratic with the confusing A's and C's. Okay, and instead you can truncate it here. So we do the same trick. dg by dq is equal to A T minus TC Q plus B Q cubed. We factorize that out, so it's Q times A T minus TC plus BQ squared equals 0. And all of a sudden, you either get Q is equal to 0, that's always going to be a solution here, or this thing here is equal to 0, in which case you have Q squared is equal to minus A over B times T minus TC. Okay. So if we were to go back, I'm not going to do it now, but I showed you a first order and a second order and a tricritical version of how phase transitions occur. This is the prediction of the second order. All right, tricritical. So B is negative, gives you first order. B is positive, gives you second order. What happens if B is equal to 0? It's right in between. So if B is equal to 0, then you do need a positive C parameter. And so we'll put on C over 6, q to the 6. Get rid of this because B is equal to 0. And we can do the same thing, do the derivatives. This will change. This will become C q to the 5th. This will become C q to the 4th. Oop. And so this will become a quartic instead of a quadratic. Okay. So if you see order parameter developing like this, it's first order. If you see it developing sort of strongly like this, you don't know, you can map it onto a parabola or you can map it onto a quartic function. And if it's a parabola, it'll be second order. If it's a quartic function, it'll be tricritical, which is this directly in between first order and second order. Okay, so ironically, yeah. All right. So successes of LGD theory, I've only done the first one. I'm going to give you these notes anyway, so don't worry about it. But I wanted to show you why it was so cool for ferroelectrics, and I think certainly I can probably cover the next two in the time available. So yes, it predicts first order, second order, and tricritical. Now let's go on to the Curie-Weiss response. And in this case, let's, instead of dealing with Q as the order parameter, let's call it like it is in a proper ferroelectric and call it P, where P is the polarization. Crucially, it's an order parameter, so it's not the polarization. It is the normalized polarization to the fully transformed low temperature state, low symmetry state. Okay, so don't fall into that trap. So P is just a number or a parameter between 0 and 1, and it's going to substitute in here for what we had been using as being Q. Okay. All right, this is where I think things start to get quite interesting. So here we have our free energy statement is equal to A over 2 T minus Tc P squared plus B over 4 P to the 4th. I'm going to leave it as second order just because it saves time. All right, if I apply an electric field to this system, then there will be an additional energy term that I need to add in. And that energy term must be such that the polar direction that is parallel to the electric field is stabilized. The polarization direction that is opposite to the electric field is not stabilized. You break the degeneracy of these two polar states being identical because now one of them is aligned with the electric field and the other is not. It's anti-aligned. Okay. So in order to represent that breaking of degeneracy, we put in this additional term, minus EP. Now the field is a force. The polarization is an effect. Force times distance moved by effect. Force times distance moved by force is work done. So there's no doubt that electric field times polarization is the multiplication of two so-called conjugate variables. So this creates an energy term. I was having a lesson, and I'm really glad I had it. It was very demeaning. I'm glad I had it. So I was talking to, I'd love to get on to Arkady Levenyuk's stuff later on. But he said, look, be careful. This is not really, don't think of this as work done. This is the energy payoff for the polarization aligning with the applied electric field. And crucially, what it shows you here is that if E is positive and P is positive, then that gives you a positive multiplication. And so the minus a positive number is a negative number. So that reduces the free energy. So the free energy will be lowered if the electric field and the polarization are both positive. Equally, they can be both negative. But the point is that this minus term requires this to be a positive term when you multiply these two things together, meaning that if the field and the polarization are anti-aligned, that'll be positive field, negative polarization. That gives you a negative number. And then this negative makes that a positive thing, which is adding to the energy. If this is a multiplication that is positive, it's going to be a negative overall, and so that is reducing the energy. And that is that's the mechanism by which we can sensibly allow the breaking of the degeneracy here. Okay, let's do the normal thing. Let's search for equilibrium. So we set that equal to 0. We have A T minus TC, P plus B PQ plus minus E, all right? Then we say, all right, well, that equals 0, so I can rearrange that, take the minus E over to the other side, or add field to both sides, and end up with a statement for okay. So this is the relationship between the field and the polarization under equilibrium. All right, susceptibility. So the susceptibility, I used to, I'm not even joking, I used to lie awake at nights worrying about susceptibility. And in the end, I found out that it was just how susceptible a system was. So the susceptibility here, if you apply an electric field, is how much polarization you develop for that electric field, how susceptible the system is to developing polarization under the application of an electric field. So if I were to formally write it out, susceptibility is the change in polarization with respect to the field. Now this is tricky. We're going to try and calculate the susceptibility, but we have an expression that's explicit for field and implicit for polarization. So the way we're going to deal with this is re-express the inverse susceptibility as dE by dP, and then be able to deal with it. So we take dE by dP. We know that that's equal to the inverse susceptibility, and that's going to be just equal to A T minus TC times P's gone plus 3BP squared. That's the inverse susceptibility, so the susceptibility is just 1 over that. Excuse me. Ooh. Okay. So we have an expression, explicit expression for the susceptibility, the susceptibility of the polarization in this ferroelectric to applied electric field. Above Tc, P is equal to 0, and so this just comes out as 1 over A T minus Tc. That is the Curie-Weiss law. So if we look at, this is a measurement done in our lab for barium tightening, ironically. Tc is about 120. And you can see here that this linear function, decreasing function as you go towards Tc from above Tc, is entirely commensurate with this reciprocal susceptibility prediction. I should also say that for a second order phase transition, if we put in the equilibrium value of polarization here and worked it through, you would end up with the same sort of expression, but it'd be 1 over minus 2A T minus Tc. So the gradient goes from positive to negative, and it actually increases by 2. It might be 2 over, I might have got that wrong. Okay, and you can see here that this is a shallow gradient. This is a relatively steep gradient as you go from above Tc to below Tc. Okay, pretty cool. So Landau's working. This is the one I want to give you, and then I'm going to be quiet. Okay, so the characteristic of a ferroelectric is the hysteresis loop. I want to show you that Landau-Ginzburg-Devonshire can predict the existence of the hysteresis loop. So we took free energy whenever we applied an electric field. We find the equilibrium condition, and this is what we find, that the equilibrium value of the field versus polarization can be given by this expression. Now let's look at the free energy in the absence of a field. Tc P squared plus B over 4 P to the 4th. So in the absence of a field, dG by dP, no field, is equal to A T minus Tc P plus B P cubed. Okay, look, this is what I want you to see. The derivative of the free energy with respect to polarization in the absence of a field is the same as the equilibrium value of the field in the presence of the field. Okay. So if I want to determine the equilibrium behavior of the field as a function of polarization, all I have to do is imagine there is no field, take the derivative of the free energy function without a field, and then substitute that derivative with it being field. Okay, I'm going to show you graphically how this works. Okay. So in the absence of a field, we're back to the old free energy function that we started with. So here we have free energy. It's a function of order parameter. No field. Below Tc, this is going to look something like this. Okay, we have a negative a over 2 t minus Tc q squared. We have a positive b q to the fourth. Now let's take the derivative of this. So here we have dg by dp, remembering that the only reason we're after the derivative in the absence of the field is that it actually represents the equilibrium field. So this is going to be equivalent to the field under equilibrium. Okay, take the derivative of this. This is quite strongly negative. This is getting less negative. At this point, it's 0. At this point, it's 0. So it's gone negative, positive, 0. At this point, it's also 0. But it's gone negative at this point, and then it comes around and goes positive. Okay, so that is the derivative of the Landau expression in the absence of a field. And under equilibrium, it equals the function of the field as a function of polarization. Now what I'm going to do is I'm going to take this, I'm going to rip it literally out of the plane of the blackboard. I'm going to probably move around here and tip it up like this. I don't know what I'm going to do. It's like a trump. I don't know what I'm going to do. But I'm going to do some kind of like geometric transformation of this in order to get a different plot, which is, I put Q again, P as a function of field. And when I do that, it'll look something like this. This S, characteristic S. Okay, and this is literally this function, but re-expressed. So it's no longer strictly a function because the vertical axis now can have multiple values. All right, I saved the red chalk for this. So now let's look at how you might measure this, this S function in the lab. So we start off here at very strong negative field. We're going to decrease the field towards 0. Then we're going to increase the field beyond 0 until this point. And at that point, and we don't know where it is, we're going to increase the positive field further. Okay? So we are, unbeknownst to ourselves, we're going to directly move from this point in this function to this point up here, if I've drawn that correctly. Okay. And then we're going to move up here in terms of our measurement of the polarization. Then we're going to start a high field. We're going to go down in field. We're going to reach this point in negative field. We're going to continue to increase the field negatively. But at this point, because we increase the field further in the negative direction, we immediately go down to here. Okay? So what I'm hoping you can see, and it's a mic drop moment, and we're going to just leave it at this, is that Landau-Ginzburg-Devonshire theory has accurately predicted the existence of the hysteresis loop in a ferroelectric. And there's so many other things the LGD can predict. They'll be in the notes, and you can look at them online. My favorite, the one I didn't get onto, but my favorite, I think, is the improper ferroelectric phase transitions. I can't remember. It was you had mentioned this. So if the primary order parameter is not polarization, but something else, we'll call it Q, then you can go through the mathematics again, and you can develop an expression for the development of P as a function of temperature. And you see that it linearly, or can linearly develop below Tc, rather than quadratically or quartically or discontinuously. All right, I got to leave it there. Time is up, but I'll take any questions.